Hi, it's Professor McDonald, and today is Thursday, so I am working on student questions in my Lumen OHM inbox, as I do typically on Mondays and Thursdays. So this question came from a student who said that they couldn't figure out how to find the comparison value to know whether the correlation was significant. But I'll go through the whole problem, starting with copying the information over to Excel. And let's read the problem. It says annual high temperatures in a certain location have been tracked for several years. Let X represent the year. Okay, so X is the year. And Y is the temperature, the high temperature for that year. All right, so we've got our data labeled, helps to know what's what. Now, obviously, it's not year one, it's 1 year past a certain starting point, and I believe that would be 1995 because it goes along with another problem that was similar. And then it says, at the 0.05 significance level, does the data show significant linear correlation between X and Y? So what we need for this is to calculate the linear correlation coefficient by using the Correl function in Excel. Now, once you start typing in a few letters, you'll see things pop up as suggestions. You can double click it, or you can just type it in if you already know what it is. Sometimes I just type them in because I feel like it's faster, and then put a parenthesis, and you're set. Then it's going to ask you for an array, array 1, comma, array 2. So array 1 is all my x's, comma, array 2 is all my y's, enter. So there is my linear correlation coefficient. This is a test statistic because I'm going to use it. First of all, it's a statistic, a measurement from a sample rather than a population. And second of all, it's a test statistic because I'm going to use it to do a test. I'm going to test for significant linear correlation. Now, even though the problem doesn't ask us to do it, I think it helps students to see what we mean by linear correlation. If you select your data and go up to Insert and Charts and choose the scatter plot, then you can see how those dots trend when you plot them on an XY plane. And there is somewhat of a linear correlation here that I can visually identify, but it's not super strong. They're not making a very beautiful line. They're kind of a little bit off. So there's a nice line there, there's a nice line there, but overall there is a line there. And we can even add a trend line by clicking on the dots, right click and add trend line. And then make sure it's set on linear so you get a line, and then click the last two boxes to display the equation of the fit line and the R squared value, which measures the goodness of fit. All right, now, like I said, for this problem, they didn't ask us to do this step. We didn't need any of this information to answer the question, but in some problems that are similar to this one, you would be asked to do that. So that's how you do it. And now that I can see that there's linear correlation, it makes sense that my correlation coefficient is 0.753 or 0.754, which you can think of kind of like a percentage. Think of it like 75.4% of a linear trend here. Now, you might say to yourself, well, that seems pretty good to me, so I'm going to say that this is a good linear correlation. But we need to compare it to a comparison value from the critical R table. So I'm going to color code a little bit here so we can keep some things straight. First of all, the test statistic is from our data and we calculated it. This other value that we're going to find is also called R, but it's not a test statistic that is calculated from the data. It's a comparison value, which we call a critical value, from a table. Now that table is in your packet for test 1. It's also linked here under the lesson 1 linear correlation learning module. So let's go ahead and open that up. And it's very simply laid out. On the left, you have the degrees of freedom, And you don't need to worry about what degrees of freedom are yet. I don't think you guys are ready to learn about that concept. It's a little bit advanced. We will learn more about that later, but it's based on your sample size minus 2. And what it really does for us is if we only have a little bit of data, it makes our critical values higher. And if you have a lot of data, it makes your critical values lower and lower. And that's because you don't need to see as much linear strength in your measurement if you have a lot more information. Because the more information you have, the more reliable your results are and the more relaxed you can be. So what these values are goalposts. They are the goal that we're going to set to say whether or not we have enough linear correlation in our sample. So we need to look at a couple of things. We need to look at the sample size to choose which row to look in, and we need to choose the significance level across the top here to know which column to look in. So looking back at the problem, we have 1, 2, 3, 4, 5, 6, 7, 8 rows of data, 8 pairs of x comma y coordinates. So our sample size is 8, and that means our degrees of freedom is 6. So we're going to be looking here in this row, the 6th row, for our critical value. The second thing we need to know is which level of significance we want. And that also determines how strong your results need to be. So here in this problem, they've specified that we should use a 0.05 significance level. So we'll be looking in this column here, the second column. All right, now in the 6th row and the second column, here I find my critical value, 0.707. Okay, so I'll just put that there. And I'm also going to put the other information that our sample size was 8, and that made our degrees of freedom n minus 2, which is 6. All right, so our critical value, I usually color code it in red just to keep the two R values separate in my mind. Green I usually use to indicate it came from the sample, and red I use to indicate that it's my critical, my comparison value that I have to meet or beat. All right, so now that we have that, we're comparing this value from the data to this value. And we need to see that we have stronger correlation in our data than the minimum requirement. Now, another way you can look at this is by drawing a number line to represent the R axis. So I'm going to just draw, please excuse my handwriting, I'm writing at a weird angle on a slippery screen, so it's not beautiful, but this represents our correlation. And in the center, if you have 0, that means you have no linear correlation. But if it's close to +1, that's perfect. Positive linear correlation, which means you would see the dots make a perfectly straight line, and it would be going up from left to right. Just like if you can remember from algebra, when you did y equals mx plus b, if the slope was positive, then it would be going uphill from left to right. And notice here that our trend line that fits our dots has a positive slope, the number attached to x. So it's not the same thing, our slope is not the same thing as our R value, but when the R value is calculated, the slope is part of that calculation, so they share the same sign. Now, if you are close to -1, that is also perfect linear correlation, except negative, so that would be a trend going downhill from left to right. Again, please excuse my handwriting. All right, so that's what we're looking at. That's the scale. Now, where do our numbers fall on that scale? We know we have to meet or beat 0.707. So you might say that your critical value is somewhere around here, 0.707, critical value. And now looking at our test statistic of 0.754, that is closer to +1, the test statistic, is closer to +1 than the critical value is. So we've made it. We have significant linear correlation. So based on that, we answer the question, yes, there is significant correlation. And so the next question is the same deal. If you regenerate these, you can do them as many times as you want, but we'll go on to the next question. Well, it turns out that I went and looked and there were no more questions from my online students in my inbox, so that is our video for the day. So I hope that helped, and I'll see you in the next video or potentially in office hours if you need to come by and work with me there. Have a great day and a great weekend.